So I'm Thomas. I've been working on Triton for about a bit more than 2 years, and today I'm going to be talking about the state of the union, and Phil is going to join me in a few minutes, and also brings his perspective on where the project is and where it is going. So I'll start with the most important slide. Is thank you all for being part of Triton community. The community has been growing significantly in the last few years, and I think it's beyond what anybody would have expected. And thank you all for being like a very lively community. So I think Phil will give more details on those slides, so I'll skip through those. But the main idea is that Triton is trying to be a unique kind of like piece of software in the ecosystem, and trying to get the right trade-off between productivity and performance. But I'll let Phil talk through those in a minute. So here's where we are as a community, and we see that we keep growing. The number of unique contributors keeps going up, and this is really amazing. So thank you all. And this is the graph of unique contributors for every 30 days window, and this is really amazing to see it continue to grow over time. And this is where we are doing how we're doing in terms of code complexity. So for us, really in Triton, amount of code is something we're trying to limit. We're trying to keep our simplicity. We see that I think we're doing okay. We've seen the backend number of lines of code has been growing significantly because we've been doing a lot of generalization and some refactoring, and I'll talk a little more about those in a minute. But I think this is a decent space, and we've seen a few drops where a bit more than a year ago we did some refactoring to try to keep things under control. And I think we're doing well. I'm definitely looking forward to hear about how people think. Triton has been getting more complex, but we can talk about that in the happy hours. And I'll also let Phil talk about that, but one of the big achievements we've done in the recent past is open sourcing some of our MOE kernels in Triton repo, and that gives really good examples of how Triton can be used, and those are actual production-ready kernels that are used in GPT-OSS and can be used in other models. But yeah, so here's the agenda of the talk, but I'll skip through that also. Let Phil talk about it in a minute. So I wanted to talk about some of the points that Phil had pointed out last year in the State of the Union, and there was quite a few fundamental problems in Triton that were yet to be addressed, and I wanted to do a check there and see how we're doing. So I think one of them was portability, and one big improvement we've done inside Triton has been pushing this thing called linear layout that has allowed us to unify all our layout representation for both register but also shared memory and tensor memory. And it's been a huge improvement at adding some robustness to our backend compiler, as well as allowing more complex transformation. Especially, it now allows us to propagate layouts through very complex shape transformation, and it allows to do quite a lot of new optimizations at the language level. Because you can now change your HBM layout and still get good performance, and change your HBM layout to even get better performance by picking layout friendly to your specific architecture. So that was definitely one of the major improvements we've done in the last year. I think tensor descriptor was also one thing Phil had pointed out last year. We did not have a good representation for array indexing. And this, I think, has also been fully solved, in my opinion. We have now a portable representation of array indexing in Triton called tensor descriptor. And as you can see in this example on the slide, that allows us to represent accesses without using pointers, and that maps directly to TMA for architectures that support it, but that also can be lowered to any other representation that your hardware supports. So that's a big improvement for portability. I think 1 year ago, we had a very ad hoc kind of representation to support TMA, and it was not portable. So it's been a major improvement. Another point that Phil had been pointing out was in terms of performance. We were seeing a lot of cliffs. So if you go back to last year's presentation, that was also an important complaint that Phil pointed out. And I think we've also done significant improvements there. The software pipeliner has been fully rewritten since last year, and it can now support arbitrary schedule. So it's not exposed at the language level, but within the compiler, it really allows growing more complexity in terms of how we pick a schedule for pipelining a loop. And really, you can see, I mean, yeah, I hate putting IRs on slides, but if you look at it, you can see that now we have this way of picking a schedule by just annotating the IR, and then the pipeliner will do the rest. And really that allows a lot more complexity into scheduling passes. And so another big thing we were missing, and that was quite a big one last year, was a solution for warp specialization, which is this new technique that modern GPUs are using to get good performance and to pipeline more aggressively the work and take advantage of the warp scheduler. And a year ago, we did not know how we were going to solve it. And within the last year, we came up with a representation that can describe at the TTGR level how warp specialization would be done, and it importantly it doesn't break our tile programming model, and we've also started adding auto-partitioning algorithms in Triton that allows to take a loop and to break it up into partitions that are going to be distributed across warps. And that's been a big collaboration across different actors in the industry. And it really allowed us to improve performance, especially on Blackwell. And there's going to be more details during NVIDIA's Blackwell talk about that part. So another big thing that was achieved in Triton in the last year has been Gluon, which, again, there's going to be a talk on Gluon later, so I'm not going to go too deep in details. But Gluon came from a realization that we needed a second tool in our tool sets to accommodate for cases where we were allowed to trade off portability for performance. And Triton is trying to be very much portable. Sometimes it's hard, sometimes it won't be fully performance portable, but portability is overall there. But that means we are not always able to get peak performance. And that was especially a big realization when we brought up Blackwell, as we were not able to get high performance on some of our attention kernels, and we realized we need another tool there. Of course, it would be awesome if Triton could generate optimal code all the time, but we are very mindful of not creating compiler magic. And that means for us, we thought having a separate tool to allow us to trade off the portability and get the peak performance was important. And the funny thing with Gluon is it actually fits very well in Triton architecture, as it retargets the low-level IR of the compiler. And thanks to all the improvements in infrastructure along linear layout and everything else, this actually works well. And we've been starting to write high-efficient kernels with Gluon that, of course, end up being target-specific, but gives a lot more control to user when they need it and when they want it. And that brought some other needs, including sanitizers. So Gluon is really interesting, but one downside is it exposes a new class of errors that don't exist on Triton, which are race conditions. As now you control your memory, you are able to use asynchronous operations, and you have to do your own synchronizations, and that means users are going to get it wrong. And race conditions are a particularly painful set of bugs to kill, and we've had quite a lot of problems with those in the past, so we're very, very much paranoid about them. And that's why we decided to develop a sanitizer that will check for concurrency problems, as well as a thread sanitizer, which is more is really for warp specialization, as we consider each warp like a thread. So that really means we need a thread sanitizer to be able to detect whether different warps are having race conditions. Continuing in the tooling part, an important piece of tool that was also significantly improved this year is Proton. Like one of the features I really like there is the fine-grained profiling, and that's quite interesting. So you can see a picture of how it roughly looks like, but it allows you to see where you're spending time in your kernel, and that allows you to tweak things and make sure things are running efficiently. It's especially important when you are doing, again, Gluon and warp specialization, where you really are on your own in terms of writing optimizations, and having this visualization makes it much, much simpler to debug and see where the performance are going. And there's also going to be a Proton talk going in detail about this. So I've been talking mostly about how we've been improving things in the last year. And I think I want to also talk a little bit about what is still not quite right in Triton and where we think we need improvements. So I think one thing we haven't quite nailed out is, for instance, the multi-CTA support. We've seen recent architectures like Hopper and Blackwell have moved to a world where now there is one extra level above CTAs, which allow you to exchange data and take advantage of features like multicast. And unfortunately, Triton currently does not have a good model to support that. So we have some experimental support for it, but in my opinion, it's still very much broken, and we haven't found the right way to make it work with Triton SPMD programming model. I think that's something I'm hoping next year we will have solved. On the Gluon side, I think we also need, there's also a lot of room for improvements with getting better helpers, getting better error message, making it a much more user-friendly tool that will allow to get perf, but still will save you from having to do just having less boilerplate to add. And right now, you very much have to reinvent a lot of things when you write Gluon kernels, including deciding how you're going to pick your layouts, how you're going to do like many of those low-level things that tend to be very often the same. All right, actually, Phil's here, so let's welcome him. And, oh, you're okay. Never mind. So actually, I only have like a couple more slides, and we can have Phil talk more. Right, so on Gluon side, yes, I think we can make the language much more user-friendly. It's a very much a new project, so obviously there are a lot of things that can be improved. But yeah, also next year, I'm hoping we'll be in a much better spot. And I think one important thing we haven't been spending a lot of time looking at, but is really how do we make downstream users happier? And right now, it's still rocky to own like a Triton downstream backends. And I mean, I'm not saying I have solutions, but we definitely want to make this simpler. And we are going to have to look at better ways to not break downstream backends every time there is a merge. And also maybe supporting pass plugins for people to have their own downstream pass. As you know, Triton cannot always accept all the contribution we would like to, because we're trying to keep complexity under control, and we are not always able to merge every PR, and I apologize for that. But I'm really hoping we can make downstream users' life much better in the near future. So I think, yeah, now let's have Phil talk a little more about some high-level concept. Okay. And this, let me get back to your slides.
Maybe we can go back to the beginning.
All right.
Just all the way to the beginning. Even before. Yeah, I think I have this thank you slide I wanted to go very quickly. So sorry for being late. I was stuck in traffic. But now I'm here. Super happy to be here for this third conference. The same place we were at like 2 years ago for the first one. Very grateful for everyone to take the time to show up and listen to what we have to say. So yeah, thank you everyone, first of all. I don't have like much to talk about, but like sort of the principle I live by, and that's like sort of governing the entire roadmap, is this idea of like not having a free lunch and like having this constant trade-off we have to grapple with between how productive we are and how performant our code is. And that's sort of like the cornerstone of, I think, how I think about all the planning we're doing, both for the team at OpenAI, but also for the project at large. And the way I look at it, especially obviously like this trade-off will change from person to person and from application to application. But let's say for like the median kernel engineer working in ML, I sort of see this as like, if you want to be like really super productive, you can use something like NumPy, but then you're kind of forced to use CPU that's slow. If you can take a little bit more complexity, you can get a lot of benefits from it with Torch. You have a little bit more runtime complexity, but you can leverage the GPU. And then like Triton's means to sit at like this place that's like a little bit less productive, but gives you like a little bit higher performance. And then you can go like all the way to the left and to the top, and you get to the lower level languages. And yeah, that's sort of how I see everything. I really believe in this concept that like at some point you cannot like become more performant without like hurting your productivity. And one thing I really like about Triton is it's gonna sound very silly, but it works. And I think now it's at the point where like we can throw like pretty much any program at it, and it will kind of work as you expect it. I think the programming model is not like really leaky. And I think like I've put like this very meaningless snippet of like doing like a bunch of reshape and transposition, and then like a top K followed by like a broadcasted reduction and another reshape and a dot and another top K. And you think if you run that, it just kind of works and behaves just as if you were like using Torch tensor instead of Triton tensors, which I think is kind of remarkable, especially because the top K is actually not implemented as a custom instruction. If you go look at the source code of the Bytonic top K, it's fully in the language with like a lot of reshaping and split and join and whatnot. And actually this code last year had, I think on Hopper we're getting like 0.5 terabytes per second, and this year we're getting like 1 terabyte per second, which is like about 30% of peak bandwidth, which I think is pretty good for something like that. And that's largely thanks to the linear layout work that Thomas talked about in his slide. So if I were to talk about this trade-off curve this year, I think the landscape has changed, and I think Triton moved up because it moved to the right and to the top because we added TMA and things like that, which improve productivity. We fixed bugs, which also improve productivity. And at the same time, we did like all this work to be able to get like better performance for like your median program. But it's still true that like if you do want like good performance for like your Blackwell attention kernel or something like that, we try to do it in the compiler, and it's like it just seemed too untractable. So we kind of just decided to rely more on lower level languages for that. So there's going to be a bunch of things that are going to be presented today. I think Helion, maybe that sits more between Triton and Torch. Then I think TLX that I think sits closer to Triton can get like higher performance with hints and so on. And then you have like, I think the much lower level languages like QDSL and Gluon that I put in the same bucket. Yeah, I didn't like, on purpose, I didn't put one to the left and the other to the right. It's up to the programmer. Some people might prefer one, some people might prefer the other. But I sort of think of these two as similar level abstraction. And then I think you still have like CUDA and SAS that gives you like more control, but take longer to write. So I think that's how I would like describe how the space has evolved over the last year. We've sort of like constantly seen like more community contributors. I don't have the graph of contributions, but there's like more and more like contributors. If you average over a rolling 30 days windows, it sort of increases, which is good. It means people are engaged in the project. As Thomas said, we don't accept every PR, but this is like committed merged PR. So even then, like there's like more and more like first-time contributors. Obviously, I'm assuming like nobody's creating like 10 GitHub accounts to fool me. Okay, and I think just if you look at the amount of code that like we have in the repo, I think it's been increasing, which yeah. I wish it didn't increase, but I guess that's kind of how software is. It kind of just keeps increasing. And usually like people don't get hired to remove code like in net. But I think overall like we've managed to keep the complexity like well factored. And I think the team hasn't burned out, so good sign. Yeah, and another thing we did is we open sourced some kernels about like 5-6 months ago. And part of why we did that, well, first of all, like I don't really spend that much time on like maintaining Triton myself. That's why like Thomas is much more like hands on the details. And I've switched like most of my focus to like managing like pretty much all LLM kernels work for OpenAI. And as part of that, I spend a lot of my time writing kernels and doing work around kernels. And I thought there would be a lot of value in open sourcing some of the kernels we used internally. There were like, I think 3 main reasons why we did that. The first one, I think the timelines lined up with GPT-OSS, and we thought it would kind of make sense to also open source kernels at the same time. This way, like VLLM was able to use like MXFP4 kernel that we open sourced. Another reason to do that is because the best thing there was before was just the tutorials. When people were looking at like canonical implementations of like a matmul, but the tutorials do cut a lot of corners, and also like they can regress performance. We just don't monitor them as closely. And another big reason is at OpenAI we sort of constantly have this issue of like having like just running into bugs that like sometimes we cannot share reproducers for, and open sourcing the kernel. I think one of the goals is like, okay, if we have a bug in the matmul, then NVIDIA can look at it, AMD can look at it. It makes everyone's life easier. And I think this has worked pretty well. There's been like several bugs that actually could only reproduce in the open source kernels. There's like a bunch of caveats. So in general, I encourage people to, and it's back to the last point about like collaboration with vendors. I think that has also allowed us to like co-optimize code together, and we've had like some success there on the matmuls. Yeah, so there's some caveats there. I think that there's like very frequent backwards breaking changes in the API of the kernels. I expect that this will stabilize. It's painful. It's even painful for me, who has to merge the things back in the OpenAI monorepo. But like, I think when we see an API is not quite right or quite fitting, I think we should be willing to take the pain to improve it, and like not just live with like something suboptimal just to avoid the backward breaking changes. So in general, I've been encouraging people to fork these kernels, and this is what VLLM has done, for example. I don't even monitor the PRs that much for Triton, to be fair. So like the directory is not like super well maintained in the sense that like I tend to look more at like the bugs I run into or my team runs into in these kernels. Yeah, and I think I also wanted to briefly talk about the agenda. Yeah, so the first bullet point, we've done it backward because I was late. But yeah, also the name of the sessions, they're like not great. I've picked them, but I couldn't find like a good name for everything because mostly there were scheduling constraints, so we had to shuffle some talks. The first one, I think we're going to start with an update on GPU mode, which I think has been like sort of extremely important, just maintaining the ecosystem around GPU programming at large, and Triton like as one of the systems. Another like I think important project for the ecosystem that's like more recent is like Helion, and Jason will talk about that as well. And Proton, Thomas mentioned this, but I think it will be nice to have a deep dive into Proton from Karen, who created the tool. A while back, he actually created the first version at OpenAI, and then like more recently rewrote it. Then we'll have a second session, I think on performance. I know it's kind of a concern that like comes back very often, is like, okay, it's nice to have productivity, but like at some point, like you need to optimize performance as well, and really get to the bottom of like really try to hit the roofline as closely as possible. And again, it's something I'm very familiar with myself because I do a lot of the kernel work at OpenAI. And I think there's like three major things. There's like the AMD backend, and I think sort of the compiler improvements that went into this backend to make the language faster, and the compiler faster in general. Then kind of a similar talk from the NVIDIA side, but maybe with like a bit more of a focus on the automatic core specialization and these kind of other techniques that are like really crucial to get like really good performance consistently across all shapes on Blackwell. And then I think, yeah, the Gluon is something that we kickstarted at OpenAI ourselves, mostly because we couldn't, as I mentioned, get the performance we wanted with flash tension on Blackwell. I mean, we could have if we had hacked the compiler enough, but we didn't want to. And we thought a more sustainable approach was to just try to expose a different point on this Pareto trade-off I mentioned. And so we made Gluon, which is a lower level language and basically a front end to TTGIR, and allows people to write low level kernels directly. And then there will be Peter and Jeff who created the language. And then the third session, I called it application. It's a bit fuzzy with ecosystem, so again, that's why I didn't name those great. But yeah, the three main items there will be the TLX language from Meta that Hong Tao will present. Then another thing that comes up all the time is like communication kernels in Triton, and so I thought would be good to include a discussion and a talk about that from Wenlei. And another one, I think at the application layer, is an update on the Liger kernels from Yanning Cheng. Yeah, so I think that's about my slides. Yes. Do we have time left?
Yeah. So yeah, we have some time left. So now I think we'll open it to questions.
Have a lot of time left. Yeah.
Yeah, we have a lot of time left for questions. So yeah, I think there are mics. Please, if you have questions, walk up to the mic and.
Yes.
Yes. Can you go to the mic?
Oh.
Oh, can you hear me?
Yeah.
Right. So I think it's good for me to see Triton is trying to be more general and to support different hardware. So like in the TTIR, most operators are like emitted as the code, which is high-level description of what the computation is, and different hardware can choose how to lower that operator. But there's some operators, for example, like the sort and top K, so they directly emit the detailed implementation, which might be optimized for GPU. So that might be not so easy for different hardware to consume. So is there any plan in the future for Triton to to make most of or all the operators just high-level description and defer the detailed implementation to different hardware, so like it could be more general? Thank you.
Yeah, I think the top K is implemented in a language today. So indeed, there's like no instruction. And I guess if you have like a hardware that for example, cannot do like reshapes or transpose well, most likely doesn't support linear layout as a first class season, most likely the top K implementation is going to either not work or be slow. I think the solution there, and then I think is probably going to be more general than just the top K, but I do think we want we want to make it easier for hardware to have their own intrinsics, and I think maybe that's what Tom was alluding to in his last slide, is there's a lot of backends that end up being downstream of Triton and kind of forking Triton. And I think today it's a bit of a pain to add operators in there intrinsics. And that would be great if it could be less painful. I think I think if there's specific requests of things we could do to make forking easier and making it easier to add intrinsics, I think it's something we're pretty open to. Does that answer the question?
Yeah, kind of.
Okay,
Thank you so much.
Hey, not that familiar with Gluon, so I'm not sure if this makes sense or is a good question, but I'm curious if you have any plans to make Gluon and Triton composable so that you can kind of get the best of both worlds and really focus on the non-portable aspect and the parts that are really important.
Yeah, that's a good question. I can tell my point of view. I think Thomas also has probably one as well. My point of view there is it's something we could do if we wanted to, but as always, there's going to be a trade-off. And I think the trade-off will be so Gluon makes the layouts explicit, for example. So that means there's two things that need to happen is whatever Gluon code you want to write, it's going to only work for a certain input layout. And then if you want to call that from Triton, the Triton compiler is going to do the layout going to have to do the layout conversion before, so that it can, so that the calling convention can be respected. And so I think that will add a cost there. And now maybe it's worth it. Like you could imagine like a case where like you have like an inner loop that takes like 95% of your time, and like maybe you don't care about having like a conversion before. It's certainly things I think we've talked about, but we haven't like really done.
Right. Yeah, I think the hard problem is really trying to find the boundary of like, because ideally you don't want to mix things because the compiler will own like shared memory and all those things for Triton. But on Gluon, it is explicit. So mixing them, you have to be a little careful. And ideally, if you could find set up a boundary of like saying, oh, like like the example Phil gave, where you just your inner loop will be written in Gluon, and then outer can be just Triton. But to be honest, I haven't found like a super good examples where that works. In general, the control will like creep, and like you'll want to like actually control your most outer loop, and that means this model doesn't work yet. So if people have example, I'm definitely curious to see.
Yeah, well, there's one counterexample of, I guess I can explain why we explored that and like we didn't do it, because we're looking, I guess, at both attention and mul, and there is like, okay, like at first you start, the boundary is going to be like, the attention in a loop, but then it's, wait, I want to overlap like the epilogue of my write back with the inner loop, so that cannot be the boundary. And before you know it, the boundary is like the first instruction of the kernel or something. That's what happened when we looked at it. But I think in principle, there could definitely be cases where there's like a more clear-cut boundary. We're very curious and interested in actually knowing these cases where we can have like value from interrupt with like a pretty clear boundary.
Hi. So one of the things that we've been noticing is that a lot of kind of the overhead we see besides like scheduling, which Gluon helps a lot with, is kind of operations in shared memory. Even Gluon seems to kind of guide programmers towards like, oh, here's like our 3 swizzled layouts that we really want you to use. Do you have any specific plans about kind of I know you can pick like a generalized linear layout, but like it doesn't really seem to be kind of recommended. Do you have specific, I guess, like plans for more interesting operations in shared memory, or kind of picking, I guess, like having more control over like, I guess, which threads are operating on specific parts of shared memory, or maybe even slices of shared memory
Yeah, I think, that's kind of what I briefly mentioned at the end. And I think the control is there in the sense like you could, like you mentioned, technically pick the exact like linear layout you want for your shared memory and the exact linear you want for your registers. And that means if you do a store or a load, there's no ambiguity in like what thread is going to access what. Now the problem is it's actually really complicated to make this decision, and you probably would have to like go on the whiteboard and do a lot of math to get there. So I think that's where we want to be able to build some better helper or some better abstractions, and to like allow you, for instance, to pick saying, okay, I have those constraints, and let me call a function that will give me exactly the layout I want to use to have no bank conflict, have like good vectorization or whatever. And I think those can very much be built on top of the current Gluon language we have right now.
Do you think, to ask a follow-up question, do you think we're missing operators in Gluon, or do you think it's more like the layouts are
I think it would probably be twofold. I wouldn't say missing operators, because I think the operators would be something that you would want like to write yourself. I think it would be that like knowing your operator. Like I think the way I would say it is that like you know how to write in CUDA, right? And it's very nice to be able to use Gluon for like, oh, I don't have to bother with like I think like when you load for like global memory, for example, like it's pretty clear usually what you want to do, and then like Gluon can Triton and Gluon can basically give you like a good layout for that. But when you're actually doing computation, usually it's not as simple as like, oh, I just want it to not be swizzled, right? Like there may be 3 ways that it could be swizzled, but like the actual thing that you're doing would want to would pick between one or the other, depending on like, oh, I'm doing a reduction in this direction or something like that.
I guess are you saying like we need like better meta programming for the layouts? Am I misunderstanding?
Yeah, I guess my question really is that like, is that something that you're interested in, right? We can always write a linear layout for what we want, right? It's just kind of annoying, right?
Yeah. That's definitely something that's on our radar. Yeah.
Okay, cool.
I think I probably put like Gluon too close to the Pareto frontier in my plot. I think it's probably like there's room to make it like just easier to use without much of a cost.
Hello, I'm curious if there's any kind of interest in supporting distributed shared memory and like GPC level programming in Gluon or Triton.
So I mean, yeah, I think that's the point I was making about multi-CTA. Is right now we don't have like it's not very well defined in Triton in the sense that Triton like programming model like, works really well within one CTA where the compiler will do the right synchronization for you and like make sure like things are happening. Across CTAs, it's a little bit broken right now. So I think we want to support that, but there's no clear design at that point.
I think we need to support that.
We need to support that at some point, for sure. I mean, there's like features like Blackwell to CTAs and things that like require it. Right now, I mean, there's some pieces there in the sense like you can, like for instance, if you do a convert layout that will cross the CTA barrier, we will use the distributed shared memory. But I wouldn't call it working. Like I don't think it's working at that point.
Yeah, is this something that would be more likely to be supported in like Gluon and kind of not supported in Triton? Or?
Yeah, I think we would start with Gluon indeed, and yeah, because it's going to be easier. And I think in Triton you have the extra complexity that the compiler needs to decide the sharding across CTAs, and that's actually a very much non-trivial decision. And it has a much bigger impact than the current decision the compiler makes about layouts. So I would definitely start with Gluon solving all the low-level like problems, and then once we're there, we can see if anybody has good ideas on how to make Triton do the rest of the work.
Cool. Yeah, I guess one thing related to this that I'm curious about is the ability to kind of sync at a GPC level. So rather than doing like warp level syncs to do a sync across GPC.
Right, that's the thing, right? Should the compiler insert those? I mean, technically, if we follow the current model, the compiler will insert those automatically. But the challenge is they are much more expensive than typical bar sync. That's very much unclear. I think that's one of the big things we have to solve this year. Yeah.
Cool, thank you.
Yeah, I think there's a question of what does it even mean for Triton to support that? It's like, I think it's not even like super well defined. It's like, does it mean like Triton needs to use multicast for like matmul, but matmul is a kernel, right? It's like, what if you have a really complicated kernel with like many dots? And it's like, what if Triton supports it and it's to slow down because of all these things? I think there's like super nuanced, whereas I think in Gluon it's just exposing it, and so it's much more tractable.
Hello. So I noticed that there's a bit of fragmentation in terms of kind of the support for like automatic work specialization, like what was included in like PyTorch is like automatic work specialization, and like what's in the main branch, which is like more focused on like Blackwell and a little less so on Hopper. So I'm wondering what like kind of the long-term vision of what specialization is in kind of the main Triton branch.
Yeah, I think it's our ideal thing there is that like different people can have different strategies for partitioning, and our focus internally was just getting the IR kind of right for work specialization. The way I think about it, and maybe it's like an unpopular opinion, but I'm not like super convinced that like in the general case of arbitrary kernels, we can get like an automatic work specialization that works sufficiently well. Now there's this separate question of, okay, if you know your kernel, like let's say you have a flash tension and you want to automatically work specialize that, I think that's possible, but that's something we're less interested in because at OpenAI, our workloads tend to change very quickly. And there's a risk that like, okay, we're going to overfit to the workloads of today and tomorrow, like it's not going to work well anymore. And I think our take there is like we'll just have really good IR for like exposing work specialization. If people want like partitioning strategies, I think like NVIDIA, Meta are building really good infrastructure for that. And then like people can make like automatic partitioners on like more case by case basis. But yeah, there's like very active discussion in terms of like the design of like automatic word specialization passes and I think this will probably be touched upon some of the talks today. Appreciate the value of being able to transition something gradually, and I think that's part of why we want to like we have this discussion on TLX, which I think is like maybe halfway in terms of how it looks. And then in terms of like the Gluon, definitely I think supporting Gluon is like very much higher effort than supporting Triton. There's someone in my team, Austin, who's done a lot of Gluon work for attention, and it's definitely like not easy. My view though is like it's something where, so OpenAI is an AI company, and like also like every decision I make, I always try to make them with the premise that models will get better at helping with this kind of tasks. That's maybe like a little bit of like avoiding the question, but I really think that like AIs will get better at helping us migrate things, and maybe like there's a future where like things are like more like incremental. If you just ask your AI to modify the Gluon a little bit to do what you want, rather than modify it by hand.
Thanks.
Hello, my name is Hong Seok from Korea. So I have a follow-up question about the adding more apps into the Triton ecosystem, etc. So I do understand that you want to be slow in adding apps for many reasons, and in any languages and any compiler framework, I think that is in general a really great approach, right? Except especially we see a diverge in like on how the AI accelerators are currently designed. Even like an NVIDIA in each generation is getting actually more features added and etc. So some other thought that we can have is making Triton more extensible in the sense that being able to like individual, let's say, AI accelerator providers being able to add their own like an apps, like an intrinsics, without like hurting the integrity of the Triton upstream, right? I think that's a kind of one way that we can think about like on how Triton to be able to continue supporting a diverse like an AI accelerators in the future. I'm wondering whether as a key maintainers and leaders of the project, have you ever put some thought on those kind of objections?
I mean, obviously we have, so we've announced, this partnership with Broadcom. I think it's no secret now that OpenAI is working on its own accelerator. But for like an anecdote, like one of the first thing I said when I heard about this project is, don't use Triton. I think sometimes like, I think forking things is okay, but like sometimes the program model is just like not fundamentally compatible with like particular hardware. And I think in general, like this discrepancy goes like way deeper than just the upsets. And so, as Thomas was saying, like we do want to make it easier to have like forks of Triton that like are extensible. But like my prior is like adding like a fancy like indexing system into Triton, probably gonna have like little value, because my experience with at least I think about like 100% of the custom accelerators I've heard of is they're like usually like not super Triton compatible at a deeper level than just the ops. It's like the memory system is different. or like the way you have to write your optimal kernel is very different, and so the portability argument doesn't really hold anymore. That's kind of my view, but like what I've also seen is it's very valuable to start from Triton when you're building a backend for accelerator, and we need to find out these pieces that people like to reuse and make them easy to reuse. And it's definitely something we want to do. It's just unclear how that translates into like actual engineering items. And if people have like, suggestions of concrete things we can do to the code base to make it like easier to extend it, it's something we're like not only super open to, but I think like interested in.
Right. Fork is definitely a direction that people can take, but I think there could be something better than a fork that Triton might be able to support intrinsically in upstream. It would be great if you can put some thought about the direction. Thank you.
Thanks.
Hi.
Okay, sorry. I think we're out of time, unfortunately.
Right. Yeah, we've run out of time. These guys will be available to take your questions, grab them during the break. So first, let's thank our speakers, Phil and Thomas, for a great overview.
Okay.
Thanks, guys. Good. So next on the schedule, we have a break. We're going to break until 10:30. Please be back 10:30 sharp for the next session. In my opinion, these breaks are the most important part of our meeting, of our conference. So this is your time to mingle and to network and to meet. We have representation from all the big companies and institutions. I also wanted to point your attention to the posters. So we have 10 submitted posters, really, really great content. And you can walk up to them, and hopefully the authors of the posters will be, somewhere there. And those posters will be there for all the breaks and also the happy hour that we have later. All right, so see you guys at 10:30. Thank you.